Hello and welcome to the Scientific Adventures of Beardman. Today we're going to be taking a look at the last section of the CAST test, known as the California Science Test, given to high school students. This will be covering questions 39 through 48. Without any further ado, in this performance task, you'll answer 6 questions. Ammonia, NH3 gas, is needed to manufacture fertilizers. NH3 is produced through an equilibrium reaction between nitrogen, N2, and hydrogen, H2 gases. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. This is the chemical equation for the production of NH3, including the heat of reaction, delta H. N2 plus 3H2 becomes 2NH3, and the heat of reaction is negative 92 kilojoules per mole. A fertilizer manufacturer wants to increase profits by shifting the reaction to the right in order to maximize the amount of NH3 produced. The manufacturer hires a chemical engineer to improve the production processes and increase NH3 yields. To start researching ways for improvement, the engineer considers Le Chatelier's principle, which can be explained by this statement. If a change in conditions causes a stress to a system at equilibrium, the system readjusts to restore the system to equilibrium. Question 39. Based on this information, what 2 changes to the system at equilibrium should the engineer suggest in order to increase the amount of ammonia produced? First choice, remove NH3 from the reaction chamber as it is produced. Decrease the temperature of the reaction chamber. Increase the temperature of the reaction chamber. Remove H2 from the reaction chamber. Remove N2 from the reaction chamber. Go ahead and pause the video and select your 2 answers now. All right, so as we take a look at this, we can see that we can either remove any one of these 3. Remember, Le Chatelier's principle said that when there's a stress, the system readjusts to restore the system. So if we got rid of N2, the system would try and produce N2, and that would be the opposite of what we want. So neither of these 2 will be options because they would make the reaction go the wrong way. But if we remove NH3, then it'll make the reaction go this direction, produce more. So therefore, remove NH3 from the reaction chamber as it's produced would be a way to shift this reaction to produce more and more NH3, because if there isn't NH3 in the system, it can't go back the other way, is another way of looking at it. Then we see that the other 2 deal with the temperature, so we need to look at the heat of reaction. Since the heat of reaction is negative, that means it's an exothermic reaction, meaning as it goes this direction, it's producing heat. So if we want it to produce more heat, we would want to do the opposite, which would be to decrease the temperature of the reaction so that it'll go this way to create more heat. Remember, again, it readjusts to restore equilibrium. All right, moving on to question number 40. All right, this is the chemical reaction for the production of NH3. We looked at this last time. The manufacturer explains to the engineer that the minimum production of NH3 should be 102 grams at equilibrium. This table shows the molar mass for each substance in the equilibrium reaction. N2 has a molar mass of 28, H2 has a molar mass of 2, and NH3 has a molar mass of 17. Question 40. Based on this information, select the correct number of grams for each reactant from the menus. If 102 grams of NH3 were produced, at least 93, 84, 51 grams of N2 and at least 51, 18, and 9 grams of H2 would have been consumed during the reaction. Go ahead and pause the video and mark your answers now. All right, so here we're going to have to do a little bit of stoichiometry. First of all, we've got 102 grams of NH3. And we know that there are 17 grams of NH3 in 1 mole from the molar mass. It's not writing super well. And this is all of NH3. Okay, so if we divide that, that gives us 6 moles. So we're trying to produce 6 moles of NH3. Well, now we got to pay attention to the coefficients up here. Okay, we can see that if we're going to get 2 ammonia molecules out of this reaction every time it progresses, what's that going to take? Well, it's going to take 1. Are we doing nitrogen first? Yes, we're doing nitrogen first. So it's going to take 1. If there's nothing there, it's a 1 nitrogen atom. So if 1 nitrogen atom produces 2 ammonia atoms, that means to get 6 ammonia atoms, we're going to need 3. That's a 3 moles of N2. Okay, and well, N2 has 28 grams, that's a G, in 1 mole. Okay, and that will give us 3 times 28, which is 60, 70, 84 grams. So we come over here and we select 84 grams. Then we need to figure out how much hydrogen. And so, well, to form 6 moles ammonia, if it takes 3 of these to make 2 of those, that means we're going to need 9 moles of H2, hydrogen, because 9 to 6 is the same ratio as 3 to 2. And we know hydrogen has a mass of 2 grams for 1 mole. And so we get 9 times 2 is 18 grams of hydrogen. This was nitrogen. And we can come up here once I get out of pen mode and select 18 grams of hydrogen would be necessary. All right, moving on to 41. So if 4 moles of N2 and 12 moles of H2 were consumed in the production of NH3, how many moles of ammonia were produced? A, 6 moles, B, 8 moles, C, 16 moles, or D, 32 moles? Pause the video and mark your answer now. All right, in question number 40, I did my mole-to-mole conversion just in my head. I said it out loud, but I'll write it down this time. So if we have 4 moles of N2, and we can see here we got a ratio of 1 to 2, we would write out our factor with the units that we have in our given in the denominator, so they cancel out, moles of N2, and we want to turn that into moles of NH3. And we can see 1 mole of N2 turns into 2 moles of NH2, and so that's going to give us 4 times 2 divided by 1, which gives us 8. So that looks like our answer is going to be 8. But let's make sure there's not a limiting factor in the amount of H2. So it says we have 12 moles of H2. I'm going to leave off some of the units because I'm crushed for space here. So 12 moles, it should be MOL, of H2. And we are converting here, and we know that 3 H2s become 2 NH3s. Again, each of these should say moles. So we take 12 times 2, that's 24, divided by 3, and we also get 8. So that means our choice will indeed be 8 moles. All right, moving on to question 42. All right, the engineer suggests changing the temperature and pressure of the reaction chamber to increase the amount of NH3 at equilibrium. The engineer shares data on alternative temperatures, pressures, and percent by volume of NH3 at equilibrium, as shown in the graphs. Percent by volume of ammonia versus temperature in degrees Celsius at 200 atmospheres of pressure. And then we see percent by volume of ammonia versus pressure in atmospheres, ATMs, at 400 degrees Celsius. Question 42 asks us, based on these data, complete the sentences by selecting the best word or phrase from the menus. To increase the amount of NH3 at equilibrium at 200 atmospheres, the manufacturer should increase, decrease, not change, the temperature of the reaction chamber. This change in temperature would shift the reaction to the left or right because this equilibrium reaction is endothermic exothermic. Go ahead and choose your 3 answers. Pause the video and choose your 3 answers now. All right, we can see here that we're dealing with 200 ATM. That matches the first graph here. So we're going to be focused on this first graph. We can also see we're talking about changing the temperature, which is what we're looking at also in this first graph. To increase the amount of ammonia at equilibrium at 200 ATM, the manufacturer should, well, we want to go to the place where more of the molecules are ammonia because we're trying to produce more ammonia. We can see that right here at 100 degrees Celsius, the percentage of ammonia is 100%. It's all ammonia. So that would definitely push it towards ammonia. So let's answer a couple questions here, then we're going to have to look somewhere else. So they should decrease the temperature, not 500, but 100. The change in temperature would shift the reaction to we might need to pop back here. Remember, producing more ammonia is moving the reaction to the right to get more ammonia. Okay, so let's go back and to the right. Because this equilibrium reaction is exothermic. We looked at that before because it had a negative delta H value. All right, so making it colder means that it tries to produce more to create more heat as it runs, and therefore you get an exothermic reaction. All right, now moving along to question 43. Using the information in both graphs, select the checkboxes to indicate whether each description is an advantage or a disadvantage for the overall production of fertilizer. The 4 things you're going to have to decide on: temperature reaction rates at low temperatures, high purchase and maintenance costs for high pressure machines, pressures higher than 200 ATM at 400 degrees Celsius produce more than a 45% yield of ammonia at equilibrium. Temperatures lower than 400 degrees Celsius at 200 atmospheres produce more than a 40% yield of NH3 at equilibrium. Go ahead and make your choices. Each one choose advantage or disadvantage. All right, so let's take a look at these 4 statements. Reduced reaction rates at low temperatures. So when things are moving slowly, they're less likely to collide in a way that reactions occur. Well, but lower temperatures are beneficial to getting more ammonia. So yes, if we reduce the temperature, we'll get more ammonia, but how long will it take? It will take longer. So the fact that it takes longer is a disadvantage. High purchase and maintenance costs for high pressure machines. Well, if it costs more, that's going to be a disadvantage. And yes, we want those things because higher pressure and lower temperature. Well, this is just higher pressure. Higher pressure gives us more ammonia. So we do want those, but it would be a disadvantage that they cost a lot. Then we look at pressures higher than 200 ATM at 400 degrees Celsius. So at 400 degrees Celsius, pressures above 200. Okay, so we see that there. Yield more 45% or higher ammonia. We want high levels of ammonia to be produced. And we can also see on this same graph, temperatures lower, or in this graph up here, temperatures lower than 400 right here. Yield 40% equilibrium at more than 40 equilibrium. So we can see that those produce a lot of ammonia as well. So that would be an advantage too. And moving on to question number 44. Using Le Chatelier's principle, explain how an increase in pressure in the system at constant temperature and volume would also disrupt the equilibrium and increase the amount of NH3 when equilibrium is restored. Enter your answer in the box provided. Go ahead and pause the video and type up your answer. All right, so if we take a look at this, we need to look at the equation here to see how pressure is going to affect what's going on. So if we have a reaction going from the left to the, excuse me, that was not very clear. How do I delete that? Let's see, let's erase. There we go. If we have a reaction going from the left side to the right side, that means we're taking 3, and then this is an assumed 1. We're taking 4 molecules of a gas. Notice both of these are gases. And we're turning it into 2 molecules. Well, that takes up less space. If we go the other direction, we're turning 2 molecules into 4. Well, more molecules would create more pressure. So if we create more pressure and the reaction, therefore, according to Le Chatelier's principle, will do the opposite, it will turn those 4 molecules back into 2 in order to relieve the pressure that was the stress that was caused. Now, that to me seems to fully answer the question. I will mention that the rubric that they give for this at the state level says that you need to mention that when there is an increase in pressure, that increases the rate of production. Well, this doesn't say anything about the rate of production. It says when equilibrium, when equilibrium is restored. Okay, and so it doesn't mention how long that's going to take. So unless I'm missing something here, the rubric, maybe that's why this is a practice question, the rubric is asking for something that's not explicitly asked for. But hopefully you understood the whole idea of turning from 4 molecules into 2 is going to relieve the pressure that you create and therefore drive it towards ammonia, which is the key. Do you see any reason why the rate at which this takes place would be part of the answer to this question? Please leave a comment in the comments below. All right, now we're headed into question 45, and this will bring us into our final 5 questions for this performance task on astronomy. In this performance task, you will answer 5 questions. In the future, high school students study the universe by working with astronauts using spacecraft that can travel long distances in a short amount of time. A student notices that satellites throughout the solar system are no longer transmitting data to the spacecraft. To recover the data for analysis, the student and the astronaut travel to each satellite. The first recovered satellite orbited the Sun and generated this graph that shows data of many stars that have already been analyzed. The luminosity and the surface temperature of each star was measured. And we see the graph right here. Based on the graph, the student should classify the Sun as which type of star? A, giant, B, supergiant, C, white dwarf, D, main sequence. Go ahead and pause the video and select your answer now. All right, so this question actually threw me for a little while because it says based on the graph, and I couldn't find any information about here as to where I should be reading on the graph. I know that the Sun is a main sequence star, so I would pick that anyways, but I finally found it, and here it is. You ready for this? it says the sun equals 1 luminosity. So we know the sun is right here. And so if we look straight across there, the white dwarfs come close, but not quite. They don't quite hit 1. And so the only thing that is in that 1 is that main sequence. So main sequence stars somewhere right in here where 1 luminosity is. That's where the sun would be. All right, moving on to question 46. The first satellite, I guess the top part's the same there. We've still got our Hertzsprung-Russell diagram. And then we see the satellite also reports the peak wavelength, lambda, of electromagnetic radiation emitted by stars in each spectral class. And so we can see a chart here of each spectral class, O, B, A, F, G, K, M, and the wavelength in nanometers of 73 through 966. And the question asks, based on the graph in the table, use the lists to select the appropriate values that will best represent the student's findings. The sun emits light with a peak wavelength of 73, 290, 527, 966 nanometers, and has a surface temperature of approximately 3,000, 6,000, 10,000, or 30,000 Kelvin. Go ahead and choose your answer, or pause the video and select your answers now. All right, before I give you the answer to this, I have to give a quick shout out to my astronomy professor at Berkeley. His name was Alex Filippenko, and when he taught me this, he taught me that I could remember the order of these spectral classes by, oh boy, Alex Filippenko gives killer midterms. Thank you, Alex Filippenko, for helping me remember that forever. Anyways, so what we have to do here is we look at the sun with its luminosity of 1. So we follow it across to our main sequence line here. And we see that at the point where that intersects the main sequence, that will lead us to a spectral class of G and a temperature of 6,000. And so that will allow us to go to our drop down and select G, which has a wavelength, peak wavelength of 527 nanometers, and has a surface temperature of 6,000. Moving on to question 47. After investigating the sun, the astronaut recovers a satellite that orbited Earth. Data of Earth's distance from the sun and orbital speed for 12 months are shown in graphs 1 and 2 respectively. All right, we see distance from the sun here, and we see the speed of Earth's orbit here. Based on graph 1 and 2, what relationship exists between Earth's distance from the sun and its orbital speed? As the distance from the sun increases or decreases, the orbital speed of Earth increases, decreases, or remains the same. Go ahead and pause the video and select your answer now. All right, so as we take a look at this, the distance from the sun and the orbital speed, let's look to begin with at the first 6 months. Okay, we can see as the distance from the sun increases, the orbital speed of the Earth decreases. So we can choose distance from the sun increases and orbital speed decreases. But wait, there's another option. If we look at months 6 through 12, then we can see the distance from the sun decreases and the speed increases. So we could also say the distance from the sun decreases and the orbital speed of the Earth increases. So we can see an inverse relationship here. As one gets bigger, the other gets smaller. Which way you choose to identify it will give you full credit regardless of what you choose. By the way, this relationship was first noticed by Johannes Kepler, and he made it one of his laws, that as the distance from the sun changes, the orbital speed changes in the opposite direction in inverse proportionality. Let's move on to question number 48. 48. After checking the distance and speed data of the other planets, the student concludes that the relationship between the two quantities agrees with the findings from Earth's satellite. The astronaut asked the student to explain the shape of the orbits the planets take as they orbit the Sun and the solar system based on the findings. Data of the Earth's distance from the Sun and orbital speed for 12 months are shown in graphs 1 and 2 respectively, the same graphs we just saw. What should the student say to the astronaut to explain the shape of the planet's orbits around the Sun? In your answer, discuss the distance from the Sun and the shape of the orbits. Enter your answer in the box provided. Go ahead and pause the video and type up your answer now. So if we have the Sun here, if the Earth is getting closer at some points and farther away at other points, and this is exaggerated, then we'll end up with an oval shape or an ellipse, as we see here. So make sure you mention that in your findings, and mention, of course, that it is closer to the Sun at some points and farther from the Sun at other points. By the way, it's farther from the Sun in somewhere around June, and it's closer to the Sun somewhere around December. It's such a small difference, it doesn't affect the temperature or anything here very much. Temperature is affected much more by the tilt of the axis, which is a totally separate comment. So here, make sure you talk about the oval or ellipse, and that it's closer to the Sun at some points and farther from the Sun at other times. All right, so moving on to question 49. While orbiting Earth, the student uses the spacecraft to examine the wavelength of light emitted from a distant star. The student found that the star is actually orange in color, but appears to be red in color when observed. This figure represents the wavelength of light emitted by the orange star. To investigate why the light from the star appears red when the star is actually orange, the student refers to this table that relates to wavelength and color. 49, Part A. Compared to the orange wavelength of light emitted from the star, which wave diagram best represents the observed red color of light? And Part B, based on the student's observations, complete the explanation by selecting the best words or phrases from the list. The star emitted orange light, but red light was observed because it is evolving into a red giant, evolving into a white dwarf, moving closer to the student's location, moving away from the student's location. This explanation supports the Big Bang theory because it provides evidence that the universe is unchanging, contracting, or expanding. Select your answer, pause the video, and select your answers now. Okay, so we can see here that, we can see here, as soon as I get this out of the way, we can see that the red light has a longer wavelength, 620 to 700. So that's a longer wavelength. So we want something with a longer wavelength. Remember, for wavelength, we measure from crest to crest. So if we stretch out this wavelength, the crest should be farther apart. And that's like what we see in example A here. B would be the same wavelength. It would still be orange. And C and D would be yellow, green, blue, or violet because the wavelengths are getting shorter or closer together. Moving on to part B. Based on the star emitted orange light but red was observed because it is, and this happens because of something called the Doppler effect. Because each wave is being released from a little bit farther away, that spreads them out. So moving away from the student's location would be the best choice here. And this shows that the universe is expanding because everything is redshifted. It means that everything is moving away from us. Now, a couple things about the wording here. First of all, when we see the word distant star, that has to mean a star that's so far away that it's out of our galaxy, perhaps even out of our galactic cluster, because our galaxy doesn't expand as the universe is expanding, but the space in between the galaxies is what's expanding. So as long as it's truly that distant, there's not a problem there. The other thing that I have a slight problem with is saying that it's moving away from the student's location. It would probably be better to say the space in between the star and the student was expanding. It's a very egocentric thing to say that everything's moving away from us. Really, the whole universe is expanding. The spaces between is expanding, and that causes the stretching of the wavelengths. Thank you for learning with us here on the Scientific Adventures of Beardman. This concludes all 49 questions in the California Science Test for high school students, the CAST practice test. I hope you've learned a lot. If you've enjoyed it, please click the like and subscribe. If you're actually taking the test online, feel free to go through here and submit your test. And we'll catch you the next time on the Scientific Adventures of Beardman.